Okay, everybody, I got 6:30, so we're going to get underway. So the plan tonight is we're going to wrap up chapter 11, move on to chapter 12, and I think probably get close to finishing that. There's not a lot of ideas that we use within that. And so I wanted to use that also as an opportunity to do a little bit of review. So let's begin by wrapping up here chapter 11. Last time we were looking at some properties of liquids. It's calling it select properties. I mean, there's a lot of different ways we can characterize liquids, but we discussed viscosity, surface tension, and capillary action as 3 examples. And then we moved on to describing this property of vapor pressure. And when I think about vapor pressure, in a way, I think that's related to both liquid and the gas. It was describing this dynamic equilibrium, and you could think about it as a property of a liquid too, because when we think about the vapor pressure, yes, it was the pressure that we had exerted by the gas, but that was related back to the intermolecular forces that were holding the liquid together. So that's why I say, in a way, I think about vapor pressure as being related to both of those. And, being related to more than one thing, that's not really unusual. When I think about melting, that phase change between a solid and a liquid, or its reverse, freezing, both of those are in terms of 2 phases as well, right? So I don't think it's simply under a single one. When I'm thinking about vapor pressure, I think it's encapsulating both aspects of the liquid and of the gas. So we're going to explore that a little bit more. We're also going to look this evening at a description of phase changes and phase diagrams. Now, to give you a little heads up here as far as resources headed into the exam, this is what I have available. So as you note, and as I've mentioned in the past, within perusal, I have a series of optional assignments that I'm trying to narrow your focus from earlier material. We have a cumulative exam coming up. And so that's why I've got these series of optional ones where I try to return to ideas in chapters 1, 2, 3, 7, to try to give you a subset of the information that I think is most important. Some folks are using that, and if you want to continue to use that, that's great. Also added within Carmen, if you recall, there's a module where we have different practice exams. So in Carmen, there's now information in the practice exam pertaining to the final exam. So within here, these are resources that my colleague, Dr. Stolfus, has put together. He's been really working hard on compiling all the information for the different practice exams. And so he put together this guideline, this set of resources that we can use as well. So it's like the previous practice exams, where there's information as far as what the objectives are. There's examples that are worked through. There's also information that has been put into mastering. The information that is put into mastering as practice tests, it's not for credit. It's optional though, but it's linked to these other resources that he has put together. If you look within the schedule now, I just updated this today. This is where we're at within mastering right now. I bumped the one that had been due on Monday to Wednesday that involved chapter 11 and a little bit of review. So if you've already done that, great. If you still need to get to that, you still have an opportunity to. That's the last assignment that we have within mastering that's for points. We're also done with everything within perusal. So both of those aspects for points, this is the end of the road for that. I added this one that's coordinated with what Dr. Stolfus has put together. That is a final exam preparation one. This relies heavily on the practice worked exercises that are within the e-text. That's entirely optional. Okay, it will show up as being worth points. It's not worth points at all. It's entirely optional. The setup within there, it includes more than 80 questions. It always gives me the estimated time. It's more than 500 minutes worth of time. This is not meant to replicate what your actual test is going to be. This is our effort to look within mastering and find good representative questions that are related to the different topics. This is if you want to authentically test yourself, give it a try, okay? For any of these, I think what I would do is I would return first to trying to say, well, what are the important topics? That's what I was trying to narrow your focus within perusal. I know a lot of times students like to say, well, let me answer questions. And if I answer questions, I must know the content. I think in a cumulative test, that's a difficult way to do it. I would start by saying, well, what are the ideas I need to know? What are the learning objectives? Let's start with that, because if you start in the other direction, say, well, let me just answer questions. Man, I don't know about you. I don't want to spend 500 minutes trying to answer questions, none of which are going to actually be on my test. So I'm not saying this isn't a useful resource. It can be a useful resource, but for all of these, you have to use them thoughtfully. I think you're all really good learners by this point. If I can help in the process, please let me know. But these are what you'll find in both perusal and within Carmen, linked to mastering. Once again, this massive one at the end, it's entirely optional. Use that as a resource if you're going to find it helpful, but it's not for points within the homework system for you. Now, where we were at then last time, ideas that we were wrapping up within chapter 11. We were looking at different phase changes between solid, liquids, and gases. We were identifying ones that might be endothermic or exothermic. So we wanted to be familiar with each of the different phase changes and whether it's endothermic or exothermic. We also looked at, well, what if we were beginning with the solid and we wanted to take it all the way to the gas, or the other direction? If we started with a gas and we wanted to go all the way back to the solid. So if we were tracking it through all endothermic or all exothermic, what would be involved with the heat? And we looked at a curve like this, where in this example with ice, we could start it out where we initially were heating the ice. The ice would melt, we would be heating the water would vaporize, and then we could raise the temperature of the steam as heat was being added. Specific heat would involve these different upslopes if we were looking at the liquid, the solid, or the gas. And the horizontal ones, those were where the phase changes took place. And during the phase change, we saw the temperature wasn't rising. It was flat there, because even though we're adding energy in the form of heat, it's not changing the temperature because it's changing the potential energy instead. It's changing the arrangement, the structure of the particles there. So we'd see along the plateau, in one case, we'd have a combination of solid and liquid, and along another plateau, a combination of the liquid and the vapor. This slide here has a lot of information where we looked at a few different aspects of this process of going from the liquid to the gas. And we saw that we had to overcome the forces of attraction, in this example here with the boiling water. We had to have sufficient kinetic energy to overcome those. But we also had to consider, well, was there an opposing pressure for this? Was there something blocking the particles from going from a liquid to a gas? I think both of those have to take place. We have to have sufficient kinetic energy for the particles to move away, and we had to have a spot for them to go. That idea of a spot for them to go, now we're starting to think about, what does it mean to go from the liquid to the vapor, and think about the vapor there. So we looked at this example, and this is close to where we were wrapping up, where we were considering what happens if you have an evacuated container and you allow some liquid to go into it. The liquid then vaporizes. We discussed the ease with which something can vaporize, going from the liquid to the vapor, and we introduced this term of, it was volatile. A volatile liquid is one that easily vaporizes. It's not very strongly held together in the liquid, so it more readily goes into the gas. I'd say a volatile liquid would be one with weak intermolecular forces holding it together as the liquid. Eventually, we'll reach an equilibrium. We have them going from the liquid to the gas and from the gas to the liquid, and the rates are equal and opposite to each other. So that's what it means when it says system comes to equilibrium. There's a dynamic back and forth. It's not stopping, but it's not changing net overall, because we have them going back and forth, equal and opposite within there. This resulting pressure that you have, this is what we call the vapor pressure. So we're moving here now to some new ideas. So within this one, the vapor pressure, it depends on two things. It's a property of the substance, meaning, well, what liquid did you initially put into the container? It's a property of that substance and also of the temperature. It doesn't depend on the volume of the container. This is not PV equals nRT. If I did this exact same experiment here, and in the bottom, I had a larger sphere that was a larger flask holding this combination of liquid and gas, it would reach the same vapor pressure, okay? It doesn't depend at all on the volume or the size of the container. The two variables are, what is the substance that you're putting in there and what is the temperature? The vapor pressure will be smaller when there are strong intermolecular forces. So let's think about that for a second. If you've got strong intermolecular forces, it would be staying together more as the liquid. It's not going into the vapor as readily. It's more staying together as a liquid because there are strong intermolecular forces holding it together. The vapor pressure is considering, well, how much of it do we have in the vapor exerting this pressure? So this is why this is the one property we have that is somewhat backwards, meaning strong intermolecular forces meant a smaller vapor pressure, because we're thinking about it from the other side. We're thinking about it in terms of the vapor. So it makes sense at the particle level. We just got to be careful with that description. That is discussing now the property of the substance. What about the temperature part? So what do you think here? Will the vapor pressure increase or decrease as the temperature goes up? Let me send you a polling question on that one. Does the vapor pressure increase or decrease as the temperature increases? Now, in a way, as I'm thinking about this, I'm thinking about raising the temperature for everything in the container, meaning I'm not thinking about just raising the temperature of the liquid or just raising the temperature of the gas. I'm raising the temperature of the entire substance. And I'm asking myself, okay, by raising the temperature of the whole thing, will that lead to having more in the vapor or less in the vapor? That's how I'm trying to answer this one. And right now, majority of folks are saying it's going to increase the vapor pressure. It will increase the vapor pressure when the temperature of the system goes up. I like the reasoning on that. We're looking at this dynamic equilibrium between the liquid and the gas. By increasing the temperature, we're increasing the kinetic energy, the motion of the particles, and that will allow more of it to go and escape the surface and go into the gas, and the vapor pressure then increases. Completely agree with your analysis there. In fact, this is the vapor pressure curve for H2O as a function of temperature. Higher temperature, higher kinetic energy, that's putting more particles in the gas space. So as you see, it has a slope going up. Temperature goes up, vapor pressure is going up. Now, if you look at this one for water, the vapor pressure of 1 atmosphere, if they take it over, it intersects right there at 100 degrees C. That's not an accident. That's the boiling point of water. The normal boiling point is when a liquid's vapor pressure reaches 1 atmosphere. That's in a way how we define when something boils. Something boils when that liquid's vapor pressure equals the opposing atmosphere that you have. That's a pretty cool phenomena, okay? We started by thinking about vapor pressure in that sealed up container, but we can also think about vapor pressure, not when it's in a sealed up container, but when it's in an open container, when it's on the stove, when it's in a beaker. A solution boils when its vapor pressure equals the opposing pressure from the air that's there. That's a cool way to define the boiling point. Now, this idea normal, that's not just saying, I'm not saying that just in a cavalier way, like, oh, the usual or something. Normal here is being defined very specifically. Normal means that the opposing pressure there is 1 atmosphere. Okay, so the normal boiling point of anything is when the vapor pressure reaches 1 atmosphere or 760 torr, same thing. That's our description for what the normal boiling point of something is. Now, this idea, notice that it was exerting a vapor pressure all along the way here. It eventually reached 1 atmosphere, but there was some going into the vapor, even at a lower temperature for water. If you think back, people had some really good questions about this a couple of videos ago in Perusal, where we were looking at phase changes and we were considering chlorine, bromine, and iodine. And in that earlier video, it said that bromine was described as having a high vapor pressure, and it showed this combination of the liquid and then the gas that was colored orange above it. It had a high vapor pressure. Well, let's think about this. Let's connect it with what we know. Bromine, it's a liquid. It's got relatively weak intermolecular forces, only dispersion forces there. That means it's quite readily going into the gas. And notice in that sealed container then, that's the gas that's being found above it. It has a high vapor pressure because it's quite readily going from the liquid into the gas above it for that particular temperature. Pretty cool connection as it comes together. Now this line right here, this vapor pressure curve, that same shape, it's true for all liquids, okay? Well, I'm overstepping a little when I say all liquids. Many liquids have that same shape curve. So notice the one here that's shown for water in blue. Ethyl alcohol, really similar, just offset a little bit. Diethyl ether, really similar. It goes off our graph a little bit, but they're all still the same shapes. Notice how this is showing the dashed line, the normal boiling point. Water has a normal boiling point of 100 degrees C. That's where its vapor pressure equals 760 torr. Ethanol is more volatile. It has weaker intermolecular forces. It boils at 78.3. That is its normal boiling point because its vapor pressure at that temperature reaches 760. That's how I want to be able to understand this figure. So if I consider diethyl ether there, compared to the others, all of these ideas fit together. I would say it's more volatile. It boils at a lower temperature. It has a lower normal boiling point. The vapor pressure is higher at any of the temperatures here, right? It's a higher vapor pressure throughout. I would attribute all of this then, it must have weaker intermolecular forces. It must have weaker intermolecular forces because it is more readily going into the vapor, exerting a higher vapor pressure, and has a boiling point that's at a lower temperature. So I'm trying to fit together all of those parts of the description. There's a picture there showing the structure for diethyl ether. So let's now practice this with something we might have on a test. This is one of the cases where I'll give you the observation, I'll give you the data, and I'm going to ask for an explanation. So here is the data. At 20 degrees C, the vapor pressure of diethyl ether is about 410 torr. For water, it is less than 10. What explains this difference? Let me send you a polling question on this one. So the data is being provided. We're comparing diethyl ether and water. What would you use to explain the difference? I really like this question because this is a really good example of this format for how these questions are set up. And after you take a second, you get your polling in on this one, I'll talk through my reasoning. Take about 10 more seconds for me. Okay, so in terms of our poll here, I'll share it with you. We're really evenly split across choices. Okay, we couldn't really be more evenly split across these. No one is choosing neither, which is interesting. But the everybody's choosing a combination here. Is it dispersion? Is it hydrogen? Is it both? So let me explain how I would go about this. So first of all, if it's one where the data is provided and you're offering an explanation, I got to analyze the data first. So when I analyze the data first, diethyl ether has a higher vapor pressure than water. Whether that was listed or you give me this figure, I am going to say diethyl ether is more volatile than water. Diethyl ether has weaker intermolecular forces than water. Diethyl ether has a lower boiling point than water. All of those are telling me the diethyl ether has weaker intermolecular forces. So the first thing I'm doing is I'm analyzing the data that it provides. Okay, so I know that I have to somehow have an explanation that says diethyl ether has weaker intermolecular forces. Okay, now let's look at diethyl ether. Diethyl ether is shown here. If I compare that with water, in terms of dispersion forces, diethyl ether, I'm sure, has much greater than dispersion forces. Dispersion forces roughly match the mass, the molecular weight. And look at diethyl ether. That is so much more massive than water. It's going to be so much more polarizable. I'm absolutely sure diethyl ether wins when it comes to dispersion forces. How about hydrogen bonding? I don't see any hydrogen bonding here. Water wins on hydrogen bonding. So we're split. Diethyl ether was dominant with one. Water is dominant with the other. Okay, so what do I want to use in my explanation right there? I need to explain why water has won. I need to explain why water has stronger intermolecular forces. That's got to be due to the hydrogen bonding. That was the factor with which it was winning. It has hydrogen bonding where the diethyl ether did not. And I needed to explain why hydrogen bonding had stronger intermolecular forces. It can't be dispersion forces, because dispersion forces, diethyl ether wins on that one. That's what I mean of saying, let's first begin by looking at the property, figure out which one has stronger intermolecular forces based on the experimental data, and then turn and say, okay, what do we want to now include within our explanation? This is that type of question. Okay, this sets up with almost any different property that we had in chapter 11. Okay, I'll try to come back and practice this again next time, because I think we still need a little work on that one, that strategy, that kind of problem. Okay, now within this one, this would be like a vapor pressure curve. Okay, one question, let me double back within this one. So there was a question about diethyl ether and hydrogen bonding. In order to have hydrogen bonding, I need the hydrogen atom bonded to either nitrogen, oxygen, or fluorine. Within diethyl ether, I see a combinations of hydrogens and oxygen, but I do not have the hydrogen bonded to the oxygen. So in order to have hydrogen bonding, it needed to be bonded to either nitrogen, oxygen, or fluorine. That's not taking place in diethyl ether. Okay, so this is a vapor pressure curve. Vapor pressure where we, in a way, we could think about, well, is it a gas or is it a liquid or is it going in between? Along this line, when we're thinking about the vapor pressure, these are combinations of pressure and temperature where we have both the liquid and the gas in equilibrium with each other. Now, you could have other phase changes like this. This is what the line looks like when you are in equilibrium between the solid and the liquid. You can have an equilibrium between the solid and the gas. That's in this region right here. Each of these lines is describing the equilibrium between two different phases. If you connect all of these, this is what's leading to a phase diagram. it is showing the conditions with which you have it existing as a gas, a liquid, a solid. Along the lines, you have an equilibrium between the two phases. Couple things that we want to be familiar with within here. So first of all, there's this point called the triple point, where all three of them intersect. And way at the top right, there's what's called the critical point. Beyond that critical point, I'm showing it as a box, but it's in that region extended up there. That describes what's called a supercritical fluid. Okay, a supercritical one, it's not really a solid, liquid, or a gas. The temperature is too high for it to be a liquid, and the pressure is too high for it to be a gas. So it's sort of like a new phase, if you want to think about that. A lot of times students say, well, what does this look like? You can reach this in the lab without that much work. And in fact, if you have like a window so you can look in it, it sort of looks like a fog, okay? I mean, in a way, a fog is a combination of a liquid and a gas, like for what it appears. That's what it resembles, okay? That's in this supercritical region, beyond the critical point. At the triple point right here, a lot of times students say, well, what does that look like? Well, we know what it looks like along any of the lines, right? If I'm along this combination of a solid and a liquid, I've got, I've seen ice water before. I've got a combination of the solid and the liquid in the container at the same time, okay? We saw before what happens when we're thinking about the particle level for a solid and a liquid, or a liquid and a gas, or a solid and a gas. At the triple point, I can just envision all of those. Okay, I can draw what a particle picture looks like if I'm thinking about a solid, a liquid, or a gas. I just have all of those taking place at the same time here. That's what the triple point resembles. This is a phase diagram here for a typical solution, or a typical substance. This is showing the different ones of what it looks like at the particle level for the solid, for the liquid, and the gas. Now it's adding additional information on here. This is related to what our learning objectives are for these phase diagrams. So for a phase diagram, this is what I need you to be able to do. I need you to be able to label the axes. The x-axis is the temperature, the vertical axis is the pressure. So I need you to be able, in a sense, to make a sketch. I need you to be able to label the axes. The x is the temperature and the vertical is the pressure. I need you to be able to identify then the different regions. The different regions on this far left is the solid. Then we have the liquid, and then on the bottom right is the gas. I need you to be able to identify where the different regions are found. I need you to be able to identify or know where the different phase changes are. We talked before about being able to name them. Notice how they're all showing up on here. Solid to the gas, that was sublimation. Solid to the liquid is melting. Liquid to the gas, that's vaporization. And then we have the ones that go in reverse: deposition, freezing, condensation. So I need you to be able to, in a sense, know what those different arrows correspond to. Know where the triple point is and where the critical point is. And then also remember what we call normal. That would be going from one atmosphere and looking to see what is the melting point, what is the boiling point when we look at the intersection where it equals 1 atmosphere, or 760 torr. These are the learning objectives when it comes to recognizing and using phase diagrams. Now let me ask you about this one: identifying phase changes. So if I were to give you a blank phase diagram, would you be able to make a sketch and say, this is where the solid is, the liquid is, and the gas? So given a blank one, you don't have to put on the specific numbers. Could you make a generic one and identify where the solid, the liquid, and the gas is found? The reason I think it's so important to be able to know where the different regions are, if one of the objectives is to know the regions, well, you got to have that covered. But if a related objective is to know the phase changes, I don't know how you can know what the phase changes are unless you know where the different solid, liquid, and gas are. So I think that that's a really important skill. Most folks are saying you think you'd have a good chance with that. So notice once again, within our set, solid is on the left, the lowest temperature. Then we have the liquid, then we have the gas, and sublimation or deposition, we see the direct change from the solid to the gas and back and forth there. Now, there's other examples. Here's the phase diagram for carbon dioxide, okay? It has a lot of the same features, right? It's got a triple point, it's got a critical point. We again have the solid, the liquid, and the gas. So even though the specific values are different, it has the same features as this generic one here. Now, CO2, that was something, recall, we said under everyday conditions, it sublimes. If we look right here at 1 atmosphere, notice how it goes directly from the solid to the gas. It's below the triple point right there. So that's why CO2, cool example of something that sublimes. It goes from dry ice to carbon dioxide gas. And in our everyday experience, there's not a lot of things that seem like they directly sublime like this. Sometimes students ask, well, why is carbon dioxide so unusual? I answered it this way. Is sublimation unusual? It wouldn't be if we lived in a world with a very low pressure. On the moon, for example, almost everything sublimes, okay? Within the pressure is too low on the moon to ever reach a point right here where you'd say, oh, okay, well, now it's going to go from a solid to a liquid to a gas. If you're on the moon, everything just sublimes, okay? It's really unusual that you would have liquid water there, for example. It would go from the solid and it would just sublime and go straight to the gas. So this question of, is it unusual? I think it's unusual with our everyday experience, because certainly with water, we don't experience that way. But it just depends on the environment that you're in. Here's the curve, the phase diagram that we have for H2O. So a couple features within here. I recognize several features that the features that we know as far as where the normal boiling point and normal melting point would be. Within this set right here, this would be looking then at the crystal structure that we have that for how the solid for H2O could be set up. Couple things when we want to look at the phase diagram and think about H2O. So first of all, something that's quite novel and important is if we look at the solid here for H2O, when it is being arranged, when the molecules are arranged at the solid, it has to accommodate the hydrogen bonding. That's what all these dashed lines are indicating. That gives it a particular structure. And it turns out for H2O, in order to accommodate this, it leads to the solid having a smaller density than the liquid. Ice floats, right? We've experienced that all the time. That's not the norm. Usually, when you have a solid, it would sink to the bottom of the liquid, but ice is unusual in this respect. And in fact, if you were to go up, H2O is a little bit novel too with the slope of this line where it's looking at the intersection between the solid and the liquid. If you increase the pressure of the solid, if you go straight up, it turns out that you could begin to take the solid and turn it into a liquid. If you take an ice cube and you put it under higher pressure, you can melt it. You can turn it into liquid water. Some people point out that that's how ice skating works, that you've got your ice there and the blade is putting a very high pressure in a small area, and that melts it and gives you a surface that you're going to be able to skate on. Now, this idea here for the biologists in the group, there's thought that this idea of how ice is less dense than water, that's one of the reasons there's life on the planet. This is their argument. They point out that, okay, let's say you've got life in this pond and the temperature is getting progressively lower and lower. 20 degrees C, 5 degrees C, 0 degrees C. -5, -10. Okay, you've got a -5 with ice forming, and they notice how they say, okay, the ice now would float on the top. The ice would float on the top, and it would, in a sense, give a barrier so the life could exist underneath that. It would blanket it. They say, well, what would happen if ice sunk instead? So if ice sunk instead, well, the pond now would freeze from the bottom up. It would freeze from the bottom up, and it would kill the life that was otherwise within the water. So there's a lot of biologists that speculate and say that the reason there's life on the planet is back to this idea of how ice floats. And if it didn't float, our oceans would freeze from the bottom up, and it would kill the life in there. I'm not a biologist, but that seems like a significant property. Now, this is when I say a generic phase diagram. I see the different lines, but I don't show the different regions. So would you be able to draw an arrow? Sorry about the grammar here. Draw an arrow showing where vaporization occurs. So take a second, look at that. Think, well, where is the solid, liquid, and gas found? Okay, where would vaporization take place? I've labeled the axes with the pressure and the temperature. Where's the solid, the liquid, the gas, and where would vaporization be taking place? Now, let me give this as a poll question. Where do you think vaporization is taking place here? Think this is a select all. Take about 10 more seconds for me. Okay, a really strong consensus here, really strong consensus that both C and D are examples of vaporization. So I think that that's spot on, okay? In order to answer this, I think I first have to pause and say, okay, if you're asking about a phase change, I first need to know where is the solid, where is the liquid, where is the gas? Okay, then vaporization, I'm going from the liquid to the gas. Both of these would be ways where I could have that transition taking place. When I was along the line, I would have an equilibrium with both of them. And then as I continue on, I'm transforming it from the liquid to the gas. And I'm trying to show two different options here. I'm trying to show that you could do that by increasing the temperature, or you could do that by changing the pressure. You can reach from one region to another, as we see here, by either manipulating the pressure or the temperature. Both the pressure and the temperature are used to define the state of matter that we have. So let's think about it here. I'm going back to water. At what temperature would you say pure water boils? Let me send you that one as a polling question. At what temperature does pure water boil? Take about 10 more seconds. Okay, dominant consensus on this one. You're telling me that pure water boils at 100. Some folks are giving me combinations either above or below. And I've got two people that said, I don't know, I need more information. Now, I'm really interested with the people that said, I don't know, I need more information. The reason I say that is I've included that as a choice on all of the questions so far. We've had about one or two people choose that each time. if I look at this diagram and I'm saying, okay, I've got water, I'm going to go from a liquid to a gas. At what temperature does that take place? I would read this and say the normal boiling point, I think, is 100 degrees C. Normal meaning the opposing pressure is 1 atmosphere. Normal meaning the vapor pressure of the liquid reaches 760 torr, or 1 atmosphere. That would be the normal boiling point. I like that idea. But in order to answer this question, I agree with the people that say, I don't know, I need more information. Because I don't know at what temperature water is boiling unless you also tell me the pressure. If it's at 1 atmosphere, yeah, it's at 100 degrees C. But what if we're not at 1 atmosphere? I could have water boil at either a lower temperature or a higher temperature. The boiling of it depends on both of those factors, okay? I need to define both the pressure and the temperature because it's going to boil when it is along this line. This line is defined by both pressure and temperature. Let me give you a demonstration. So I saw this one online. There's a lot of examples. This is a demonstration I used to do myself. So what they've done right here is they've taken a marshmallow and a beaker of water, and they placed it in a bell jar. So it's sealed up on the top, and they put a vacuum pump on this. So what they're going to do is they remove air from the jar. Marshmallow expands. To the water. How cool is that? They're not heating it a bit. They're changing the opposing pressure. That is, I'll tell you what, I find that so cool. I'm going to watch it again. Look at this one. So they're just removing the air from the container. It's causing the marshmallow first to expand. They're not heating the water at all, but they're changing the spot they are on the curve right there. For the same temperature, it now boils. The water boils when it reaches the vapor pressure of what's opposing it, and they reduce that opposing pressure. Really cool example, okay? Now, I noticed within here, there's a discussion here about pasta, okay? Now, let me go in that direction, okay? What if you wanted to have the water boil at a different temperature? A pressure cooker allows you to have the water boil at a different temperature, okay? Because the way the pressure cooker works, you put your water in here, you have it like there, and you the water would begin to boil. It goes from the liquid to the vapor. When it's in the vapor right there, then it's beginning to have a higher and higher vapor pressure above it. That's why it's all sealed up and it has the gauge right here. So in a way, you're blocking the water from going into the vapor because it's being trapped in this container. And the pressure goes up higher and higher and higher. So at that point, you're making it so the water now is not boiling at 100 degrees C. It has to be at a higher temperature in order to boil because you've got the opposing pressure on that. Now, this would be a way where you can make the water boil at a higher temperature. Let me give you the opposite. My parents, they've retired out to Colorado. Okay, I grew up in Michigan. When I was about your age, I was in college. They moved out to Colorado. Okay, so they sent this picture just the other day. Okay, they live in Estes Park. They're up near the Rocky Mountain National Park, very high altitude. When they're there, when they need to cook things in boiling water, it always takes longer. It always takes longer than it did in Michigan. It takes longer than if we were cooking something on the stovetop in water. In fact, when they get their pasta, on the side of it, it tells you how long to cook it. And it says, okay, at altitude, you have to cook it longer. Why does that happen? This is just the opposite of the pressure cooker. It's easier to boil the water at altitude, at a higher altitude. We saw that you could boil it without even adding any heat if you had your vacuum pump. In their case, the water boils at a lower temperature. It's not as hot. So when they're cooking their pasta, it takes longer. When they're cooking anything in boiling water, it takes longer there. Now, I brought up pasta. Let me share with you a pasta story. This is leading to a poll. Okay, so I need you do your best to pay attention on this one. Okay, so I mentioned my parents. I grew up in Michigan. One day, I probably just started high school. Okay, they went out to a restaurant. It's probably in Windsor, and it was an Italian restaurant. And they came home and they were all raving about the fettuccine they had. It was this pasta dish with a cream sauce and probably had some pancetta in it. But they got the recipe. They got the recipe from the chef. Okay. And so they said, hey, let's make this at home. Now, my parents, bless their heart, not the best chefs, not the best cooks, especially in like 1982 or something. They cooked almost everything in the microwave. But anyways, they had this really good fettuccine. Okay, so it entered the rotation. They'd ask me, okay, what do you want to eat on Saturday? I'm like, yeah, let's cook the fettuccine. So they would make the fettuccine, the pasta in this cream sauce, and they would dice up ham in it. Okay, so they'd be dicing ham in this pasta. And so I equated that with fettuccine. For me, fettuccine was pasta with a cream sauce with ham in it. Now pause for a second. If you're a food person, you can see where I went astray. All right. I did not understand the errors of my ways. I go to graduate school then. Okay. I still think that is the description for fettuccine. It's pasta with ham. I go to grad school. I'm at the University of Michigan. I'm going out on a date with who is eventually going to be my wife. I go to an Italian restaurant and I order the fettuccine. Okay. I order the fettuccine and it's this fettuccine dish, but I look at it and I don't see any ham on there. So I'm a little perplexed because that's what fettuccine is after all. So I got a polling question for you. What should I have done at that point? They've just served me fettuccine, but it doesn't have any ham on it. I don't know if I have this one set up as a polling question. You're gonna have to tell me in the chat, A or B. All right, A or B. What should I do? They've just given me fettuccine, but it doesn't have any ham. Do I send it back because it's not really fettuccine? Or did I have an error of some way, in some way? Yeah, I did not cause a scene. I'm sure I said to my date at the time, I said, I just don't understand this. They've served me fettuccine, but I don't see any ham here. I was completely wrong. The foodies amongst us now, no, fettuccine, no, that is a cut of the pasta, right? Just like you could have linguine or spaghettini or spaghetti or any of those are all referring to the cut. It is not referring to whether you have ham in it or not. And so I don't know why. Well, I'm glad I didn't cause a scene. I don't know why my wife ended up sticking with me on that one, because this was like such a faux pas. But I wanted to share. When I looked, here was a picture. I grabbed it off the wall. Here's a picture of me of that same age right there. So this was at my wedding shortly thereafter. Okay. We got married in Ann Arbor, outdoors, potluck. Notice the baseball mitt right there. So we could, sports outside and stuff like that. So somehow she put up with me, even though I knew absolutely nothing about when it comes to being a foodie. I've since moved on, as you know. I like my food, my carbonara, etc. But I'm going to use this maybe as inspiration. It's inspiration meaning, look how wrong I was, but I was still able to turn it around. Let's use that as inspiration, perhaps in some ways in this class. We still have an important final exam. Let's make that our fettuccine. Let's make that where if we can now get the concept right, it will be to our benefit. That's my attempt here to try to connect this somehow to chemistry stuff. I want to now move on a little bit and look at some of the ideas that we have here in in chapter 12. I'm going to use chapter 12 to begin to think back to some of the other topics that we had along the way. The ideas within chapter 12, so many brilliant ideas, but we just barely introduce a few of them. I want to use this as an opportunity to begin to review some things. So in chapter 12, it's all about solids, structure and properties of solids. You know, we live in a world of solids. Look at this, whether we're talking about technology, like a cell phone, a diamond, copper wire, glass, butter, all of these are solids. Look how dramatically different they are. I mean, oh my world. Are we talking about a diamond? Are we talking about a semiconductor of some kind? You know, the kinds of science I'm involved with, I was involved with studying solids, because solids, how you can make them and adjust their properties, just so amazing. I mean, chapter 11 is cool. Chapter 11 allowed us to explain some things, but chapter 11 was mainly about just solids, liquids, and gases, and tell me if they melt or not. I mean, that's fine. But if we really want to understand what's in our world, we got to be able to understand the structure of solids. So we're going to touch on it just a little bit, but to me, this is a part of chemistry that I'm really excited about. So within chapter 12, we have some very limited objectives. We want to be able to consider the structure and properties of different solids. That's our number one objective. I want to contrast a little bit. What do I mean when I say something is crystalline versus amorphous? Introduce what's called the unit cell and say how we can think about the density of solids. But the number one objective is this very first one, how the arrangement of the atoms, the structure, gives rise to different properties. And I want to begin to discuss this and connect it and make it, again, sort of like a review of ideas that we've seen before. So first of all, we've seen these two types of solids already, ionic solids and molecular ones. Ionic solids, as we know, are this extended lattice of cations and anions that are attracted to each other throughout. Molecular solids, we have these distinct, discrete molecules that are often held together by intermolecular forces. Both of these are things that we've looked at a lot. We saw how we have different naming schemes. We saw how we use an empirical formula for ionic solids. We've really been spending most of the semester talking about these two types. I want to add two more types to this, though. Metallic solids and what are called covalent networks. So we have a total of 4 different types of solids we want to be aware of. When we're thinking about these covalent networks, a great example, a textbook example here is a diamond. A diamond does not have discrete molecules in it. It's a continuous network of carbon-to-carbon bonds throughout. It doesn't have a distinct subset of those. It just keeps going and going and going throughout. In fact, if you look at that top one right there, you can see how it has 4 different bonds coming off of this. All of them have 4 different bonds. So what I'd like you to do for a second is let's connect this back to stuff we've been talking about. Take a second. What do you think the bond angle is within diamond? And what kind of hybridization would you have there at that particular carbon atom? Let me send you a poll on that. What do you think the hybridization is at a diamond, at the carbon atom in diamond? Is it sp, sp2, or sp3? Remember how we handled our hybridization? That was one of our bonding models, right? And we said that if we know the electron domain geometry, we can explain that by using our combination of S and P hybridized orbitals to explain the electron domain geometry. If it was linear, we were going to use the SP. If it was a trigonal planar, that would be SP2. And if it's tetrahedral, that would be SP3. It looks like within carbon here, in diamond, I see 4 different electron domains. They're all bonds within that. So I agree with the majority on that. I think the bond angle is going to be really close to our pure tetrahedral 109.5. And I think it would be sp3 hybridized carbon again and again throughout the entire structure. That's why it's saying it's a covalent network, covalent bonds throughout. And as a network, it just keeps going and going and going within 3 dimensions. What about here for the metallic solids? Metallic solid is being described as one in which there is a sharing of a network of highly delocalized electrons. That phrase, delocalized electrons. Delocalized, I think that's something we've seen before, okay? Let me send you a poll on this one. Where have we seen that before? When did we see the idea of things being delocalized? Was that when we were talking about molecular orbital theory, the lattice energy, resonance structures, the emission spectrum of hydrogen, or diamagnetism? When did we use the phrase delocalized electrons? Take about 10 more seconds for me. This one, majority of folks are saying it was pertaining to resonance structures. I agree completely, okay? Within our set right here, resonance structures, that's where we saw that when a single Lewis structure was not sufficient to explain the properties, we had to take the electrons, instead of saying they were found distinctly just in an individual bond where they were localized, they were going to be delocalized and spread. And that's where we got, remember, oftentimes fractional bond orders. Resonance structure is one in which the electrons are not being, in a sense, owned by the bond, but instead are being spread throughout. I noticed that the second most popular choice here was molecular orbital theory. I think that's a pretty good second choice. And the reason I say that, within molecular orbital theory, the electrons, we said, were no longer the properties of the atoms that they came with. They were now part of the entire molecule. So I like that idea of thinking about electrons now being part of the entire molecule, but I'm not sure I would necessarily say they are delocalized. They could still be found in distinct bonds and not spread throughout. I'm thinking about the bonding in H2, our simplest example we use molecular orbital theory for. We took the 2 electrons, they both went into a bonding molecular orbital. They're now a property of the molecule, not the atoms, but they're still found in that sigma bond. They're not delocalized in some way. I like that description. I like the thought, I could see how you might be putting those together. I think the strongest answer here, though, is resonance structures. Now, the reason I'm bringing these up is not to try to say, aha, this is like a multiple choice question for a test. I'm trying to bring these up as these are all topics that I know are relevant for the exam. Using molecular orbital theory, thinking about lattice energy and doing lattice energy rankings, thinking about the emission spectrum of hydrogen, where we saw how we could have photons being either absorbed or emitted. And when we're looking at for hydrogen, you recall how as the N value got larger, the energy levels were converging and getting closer and closer together. Diamagnetism, that was a description we saw as a property when we were looking at molecular orbital theory. And we contrasted that with paramagnetism. I'm trying to bring up here all different things that we've looked at throughout the semester. And the fact that you said delocalized is a match for the resonance, I think that that's really encouraging. I think you got a good sense for a lot of these different ideas. Now, when I'm thinking about the bonding in solids, there's 2 main classes of solids that we need to be aware of. One of them is when we're looking at what are called crystalline solids. In a crystal for the solid, the atoms are arranged in a very regular repeating pattern. It doesn't matter any of those bonds that I just mentioned, whether it's ionic, molecular, covalent network, or metallic, they all, if they are crystalline, They all have a repeating pattern. This would be an example here for a quartz, SiO2. So we see like that symmetric shape that's repeating again and again. If it's crystalline, it has a repeating shape again and again. I want to contrast that with something that is amorphous. If it's amorphous, I still have local bonds there. I still have bonds between the atoms, but I don't have this long range pattern. I don't have this long range arrangement where it's repeating again and again. It's amorphous. It lacks that shape. It lacks that degree of order. We have amorphous materials in the world around us all the time. A real classic example is a glass. A glass is an amorphous solid. Some people think of these as, it's as if you have a liquid where the atoms and molecules are together, but they're somewhat more random, and you were able to freeze that right there. You are to make that into a solid and keep the structure. In some ways, that's what an amorphous solid resembles. Now, within here, in SiO2, whether I'm looking at quartz or in the amorphous one, in the glass, there is a linkage, silicon, oxygen, silicon. It's taking place in both of these. You can't really perhaps see it within the image right here, but there is a link, silicon, oxygen, silicon within these. What do you think the bond angle would be at that oxygen? What would Vesper theory tell us? Give you a hint. We had a similar kind of linkage in H2O, right? Hydrogen, oxygen, hydrogen. What would Vesper predict? What kind of bond angle you would have at the oxygen there? Vesper theory would say, okay, you've got two lone pairs and two bonds. You would begin with an ideal tetrahedral and say, okay, the lone pairs take up a little bit more space, so it squishes it a little bit smaller. That's how we predicted bond angles. Vesper would say, yeah, it might be a little bit smaller than 109.5. I bring this one up as an example, not because you need to know what the bond angle is in SiO2, but this is one thing. I spent about 4 years of my life studying the bond angle in this. This is my most influential paper I've ever written or ever will write, where I was looking at the bond angle distribution there. Look at what the bond angle distribution is in silicon, oxygen. So for silicon, oxygen, silicon in these, it's nowhere near 109. This is what we worked, no joke, 4 or 5 years to determine. It was this distribution much more spread out, much more around 145 or so. And the reason I'm bringing this one up, not because you need to memorize or know that specific value, but many times when we are looking at Vesper and we're asked to predict bond angles, students would say, well, do I just look at the most immediate neighbors? What about the rest of the molecule? Is that important? For the ones that we've looked at, it's not important. If you're just looking at carbon, nitrogen, oxygen, these smaller atoms, all you need to do is look at that central atom and it tells the whole story. For something like this, silicon is getting a bigger one. You can't bring those as close together. So it starts to break down. Vesper doesn't work. I'm not saying this to spook you, to say, oh, well, should I freak out about Vesper not working? It will work in this class. But I'm just pointing out in real life, when people had the question, well, do I ever have to worry about what's on the outside? Once they get larger, yeah, you do. It doesn't, Vesper theory begins to break down then. Now, when you have a crystalline one, we're going to spend most of our time in this class talking about the crystalline arrangements, where we have this repeating pattern again and again. The way you can think about it is it's thinking about the smallest shape that you have that then repeats again and again. If you are thinking about it in 2 dimensions, the shape that you choose, it needs to fill up the entire space that's allowed. You could think about it sort of like if you had tiles on your bathroom floor. There's only certain shapes that you can use that will fill up all of the space without leaving holes. A square would be one example. You could have a square again and again, and it would fill up the entire space. You couldn't pick a 7-sided object, for example. It wouldn't fill up all the space. There's only certain shapes that will fill it all up. If you take a square, you could have a square again and again and again and again. It's not going to have empty space. It could fill up all of the space. That's what happens in two dimensions. That's called, it tessellates. It turns out there's only a fixed number of arrangements that you can fill up now in 3 dimensions. You can probably envision some of these. If you take a cube, like you might have if you're stacking dice together, you could have one cube and then another and another and another, and it could go in all 3 dimensions and it would fill up all the spaces. Or maybe it would be something that would be orthorhombic, or a hexagonal one would be another example. But my point is that for these crystalline ones, it's a pretty cool idea that any crystalline solid that you have, in most of our world, we have so many crystalline solids, they all get reduced down to the smallest repeating pattern. And it's not like there's an infinite number of smallest arrangements. There's a very small number of these small patterns that have to repeat again and again. I think that's remarkable. That's how the solids, the crystalline solids in our world are made of. They all have the smallest repeating pattern, which is describing the unit cell. And that unit cell just repeats again and again and again and again in X, Y, and Z to fill up all the space. This would be if we're looking at how that takes place for sodium chloride. We have this repeating pattern of like these cubes again and again, where we have sodium and chloride atoms. This is an image on the top right here of what if that repeating pattern gets big enough so you can actually hold it in your hand. So cool that it resembles what the smallest subunit has been, what the unit cell had been. I find that remarkable. Now, if I look more closely at this picture, the sodium and the chloride, they're showing them that they're different sizes. So take a second. Would you be able to explain or predict that the sodium cation is smaller than the chloride anion? Because that's definitely what they're showing in this image. And related to that, what about the neutral atoms? Is the sodium atom itself smaller than a chlorine atom? This is taking us back to ideas that we had in chapter 7. In chapter 7, we were looking at periodic properties, and we were thinking about the sizes as far as ions and neutral atoms, trying to offer explanations and making predictions. So before I go with that, can you explain this? I got 2 different questions about the cation, the anion being different sizes, and then a comparison for the neutral ones. Let me send you a poll within this. Do you think you'd be able to offer a good explanation here? Going back to the ideas from chapter 7. And as the poll comes in on this one, this is a really, I think, representative question, very representative topics that we had at the time when we were looking at chapter 7. When we were looking at periodic properties involving, first with looking at the effective nuclear charge, thinking about the size for atoms and ions, the ionization energy, and the electron affinity, all of those really closely related. And I think the size is really important at sharing results here. Most people trending from neutral to positive, thinking you could handle a question like this. If I were to look at this one and look at the different parts, first of all, if I'm comparing these ions, I always like to see where do I end up. So if I start with sodium, if it loses an electron and becomes sodium plus, it's going to be isoelectronic with neon. If I look at chlorine and it becomes chloride minus, it's going to be isoelectronic with argon. So right away, right there, I know argon much bigger than neon. The electrons are in a larger principal quantum number. So right away, if I had electrons that corresponded to the value with argon and neon, I know the argon would be bigger. And then I could also think about, well, what does it mean to have neon, but now instead of 10 protons with 11, because that's what sodium has after all, that would make it even smaller. That's, remember where we did comparisons, where we're thinking about things being isoelectronic and thinking about the size based on how many protons were present. That's how I would begin to offer my explanation first here for sodium plus and the chloride anion. When I'm thinking about the neutral ones, I see that sodium and chlorine, they're in the same row. I am thinking to myself, you know, there is a contraction as I move left to right because the effective nuclear charge is going up. I'm in the same principal quantum number, whether it's in the 3s or the 3p, but I have a contraction as I move left to right because the principal quantum number is not changing, but I'm adding more and more protons, so the effective nuclear charge is going up. That's how I would explain this contraction as I go from sodium, and then it gets all the way down smallest with argon, and then it gets bigger again when I go back to potassium because I'm now in a larger principal quantum number, and my shielding has changed again. This language of thinking about effective nuclear charge, shielding, connecting it to size, connecting it to ionization energy, definitely ideas that were important from chapter 7. So try to make that something that you return to and revisit. Now, this particular structure right here, when we think about unit cells, you might ask, well, how do we even know that? How do you know what the arrangement is? This is a really cool part of science. You can determine the structure by using X-ray diffraction. Got an X-ray diffractometer in my lab. Really common instrument used to determine the structure of solids. X-ray diffraction comes back to the wave behavior and how you can have waves interfere constructively or destructively. What you do within this one is diffraction occurs when the wavelength that you're using is similar to the spacing that you have in your structure. And it turns out the spacing in the structure between the atoms, it's similar to the wavelength of an X-ray. So you can get a resulting pattern and work back from the pattern to say, what was the arrangement then of the atoms? Anything that is crystalline, that has this repeating unit, we know about the structure from that by using X-ray diffraction. Really cool idea. I mean, back in chapter 6, we were looking at how we could have the description of light having characteristics of either a particle or a wave. And when we were thinking about it as a wave, we were thinking about the electromagnetic spectrum, the different regions of that in terms of wavelength and frequency. Take a second, see if you can do this. Place these regions of the electromagnetic spectrum in order based on energy. If you're asked to rank X-ray, microwave, blue light, and infrared, which of these is lowest in energy? Which is highest in energy? Give that a try. Now, before I share an answer on this one, let me send you a poll here that sort of has some metacognition to it. So this one, the poll says, I can order the regions of the electromagnetic spectrum in terms of energy, wavelength, frequency, and I could do related calculations, meaning I can convert between wavelength and frequency. I could use E equals H nu. I could use C equals lambda nu. Take a second, reflect on that skill. That's how we started chapter 6, if you remember. We were looking and doing calculations like this and doing rankings like this. Most folks within here, very similar to what we saw before. I'd say trending from 3 on up. This is definitely a learning objective I'd expect for a test. Lowest in energy was a microwave. Highest in energy was an X-ray. X-ray would have the highest frequency. It would have the shortest wavelength. Definitely an idea that we had back there within chapter 6. So this is looking then at different aspects of the bonding in the solids. I think we're familiar with a couple of these. What we want to do is think about how the bonding can then influence the properties, how the bonding is related to the different properties they have. But I'll tell you what, let's pick up there next time. Okay, I think folks did a really good job participating, thinking through the different parts. I'll hang around if you got questions. We're really close to finishing up ideas here within chapter 12. I want to use the opportunity in the next class to also then review and bring up some other topics. If you got specific things you want me to cover, shoot me a message and I'll try to include those. Thanks a lot, everybody.
Hey, Dr. Clark. When we talk about crystalline versus amorphous solids, are we only talking about covalent network solids and ionic solids?
No, I would say that both of those categories, they work across all of the different types that we have. It's not restricted just to one particular one. One example, a cool one, is if you have this is another cooking example. If you've got sugar, so sugar is a molecular solid. If you take your molecular solid and you heat it up and turn it so it begins to break down and become amorphous, that's what caramel is. So caramel is amorphous sugar. That would be, again, you could take any of those and turn them into something that's amorphous.
Okay, and what would, you could have even an amorphous ionic solid?
You can, but I think that if I had to think which one is the most difficult to conceptualize, it might be the ionic one, because I don't have as great a mental image of like what does an ionic liquid necessarily mean. The ones that they could have that would be amorphous, they are usually ionic, but they're not exactly like the ionic ones that we've been looking at. And the reason I say that is they would be similar, but they would have a much larger difference between the size of the cations and the anions. So that affects the structure a little bit.
Okay. And then I was looking at these three-dimensional unit cells. Why are they all? Why is like the hexagonal one still a rectangular prism? And
good question. So if you go back to that one, and it's sort of like where's the name hexagonal part comes from it. This would be one, and it's not that easy to see as you look at the top from this one. But if you take three of these, with the way the angles work, if you take three of these and put them all together, then it looks like your hexagonal, sort of like you imagine, like with a honeycomb or something, that six-sided arrangement. That's what you get if you take three of these and stick them together. That's how the angles will end up working out. That's where this name comes from for a hexagonal one. And if you take then that hexagonal one, that would be something like in that six-sided one, that could then tessellate. You could have that stack up again and again and again. But it's pointing out that in that six-sided one, it's actually made up by the smaller subset that would be inside of it. So you don't need 6 points in order to make something that ends up being hexagonal. You could have this 4-1 that then is a subset of it.
Okay, that makes sense.
Dr. Clark, what allows the covalently bonded solids to like basically have a similar arrangement as the ionic solids?
And when you say similar, what part do you mean similar? Do you mean that there's a unit cell, or what do you mean when you say similar?
That both solids are very like regular, I guess, like the structure is the same throughout.
Yeah, I would say it might not be obvious, but anything that is crystalline has a repeating pattern like you see that's being shown here in 2 dimensions for the unit cell, whether it's a molecular whether it's ionic, any of them has its smallest subunit that repeats again and again. If we look here, I want to get where I got all of them on the screen at the same time. It goes away. If we look like this metallic one, part of the pattern that it has right there is, notice how it's got 5 at the top, and then there's this layer in between, and then we have another layer at the bottom. This has this reproducing pattern again and again as well, even though they're all the same atom and it's a metallic arrangement. If we look for the carbon right below that, notice how it's showing like within this box right here, it's trying to show what the unit cell is. This would be the feature that you would then have that whole box repeating again and again and again. That's how the covalent network one would be put together. If we look at that same one here for the ionic solid or the molecular one, they're trying to show them in these boxes, not because they're stuck in the box. This would be then the part that would be repeating again and again in order to fill up all the space. I think for the ionic one, our eye just can make a little bit more sense of that, right? I think for the ionic one, we look at it and we say, oh yeah, I can see what would happen. You would just take that again and again, and it would end up, hang with me, it would end up filling up all the space. And if you got a whole bunch of the ionic ones, it would look like this much bigger arrangement. But that same thing of starting with a smaller part and having it repeat again and again in 3 dimensions, if it's crystalline, it works for all of those arrangements.
So then what dictates whether something would be like a normal molecular solid with like discrete molecules and then a covalent bonded network?
That's a good question.
Network bond.
Yeah, that's a good question. I'm trying to, it's a good question. I'm trying to give you a good answer. Both of those, if we think about it, if it's the molecular or the covalent network, there is a lot of similarity because both of those, they do have like these localized covalent bonds, right? They do have these local bonds that are right between, the neighboring atoms. The difference is in the molecular ones, eventually those stop and you get a discrete molecule. And in the covalent network one, they just keep extending on, in 3 dimensions throughout. I think as, if I'm trying to think, well, why one versus another? If you think about the diamond there, diamond's quite special because in order to have that keep going, you need to have that exact tetrahedral at each of the carbon atoms and just have that keep going and going, right? If it wasn't, you couldn't say, well, let me just choose a different angle somewhat. No, in order to have carbon be tetrahedrally coordinated throughout like that, it needs to have 4 of the neighbors again and again throughout like that. So in some ways, that is a very unique, special arrangement. If I'm thinking about carbon when it's bonded to other carbon atoms and in far more everyday things, if I've got other atoms there as well, like if I've got hydrogen atoms there as well, it might stop and form a smaller molecule rather than having just the carbon extend, throughout all of the space right there. It makes me think a little bit about, well, I mean, how do you make diamond? How is diamond made? Diamond would be made if you've got a lot of carbon there and you can compress it and just make all the carbon atoms squish and stick together. A carbon, you can make diamond by taking carbon atoms and squishing it under very high pressure. So in some ways, you can end up with that, but it's a lot easier to make other things. It's a lot easier to make carbon in other forms than it is to have the unique one that corresponds to diamond.
Right. So does that mean that in order to have a covalently network solid, or sorry, I don't know, like, you know what I mean? I'm assuming. Can that solid be made of only one atom or like one type of atom?
Yeah, really good question. There are another example would be all the same thing, would be all silicon atoms. That would be another one that would be very similar to diamond. You can also make it so it would be very similar to all silicon, but you substitute out some of the silicon for very similar elements that are found on the periodic table. So it's still largely in that same structure, but you just have slight variation to it. That second description right there of starting where it's almost all silicon, but you substitute in just a little bit, that's actually very important in terms of technology, because that's how you make semiconductors.
Okay, thank you so much for your help.
Really good questions.
Thank you.
On the practice exam for the final,
Mhm.
one of the questions was about, the dominant Lewis structure for CF2.